Okay, what I'd like to talk about now is a secant line of a function, how to calculate its average rate of change, and basically how that average rate of change begins to change as my 2 points become closer and closer to each other. So let's take a look at this. Right now, this is the graph of y equals x squared. And I have 2 points. One point is at negative 2, 4, and the other point is at 3, 9. We like to calculate the average rate of change, and I have displayed for you the secant line, which is the line that connects 2 points on a function. So I'm going to take a little screenshot of this. Let's see. Nope. Let me make that small. And okay. Oops, didn't want to turn it on. So there's the function we just had, and all I've done is change this to a screenshot setting so I can write on the graph. So average rate of change, again, is going to be defined by a few things. Let's go to draw here. This distance, which we call h, and this, which is going to be our y2 minus y1. So let's check out our calculations. So y2 is 9, y1 is 4. So 9 minus 4 equals 5. Now, for the h value, there we go. Okay, to get the h value, let me put that back because I erased it. We're going to take x2, which is 3, minus x1, which is negative 2. Always make sure that you're using parentheses when dealing with negatives. So subtracting a negative is the same as addition. So this is the same as 3 plus 2, which equals 5. So my average rate of change equals the rise over the run of my secant line, which is 1. Now notice something here. I didn't mention it earlier, but there was this other point here. This point is negative 2, 1. It's not part of the graph at all, actually. What I am showing there is when my first x value is negative 2 and connecting to whatever other x value I've chosen, I've had the computer calculate the average rate of change for us. And notice it calculated the average rate of change for us at 1. We can do it by hand, but I just set up the computer, and I'm going to show you why. If I was to calculate another average rate of change, and this time I'm going to change the x value to 2. And again, the computer says that the average rate of change should be 0. Let's go ahead and verify that real quick. And again, I'm going to do a screenshot. So we can see this and I can write on it. And there it is. So now, the average rate of change, again, is going to be y2, which is 4, minus y1. All over x2, which is 2, minus x1, which is negative 2, which gives me 0 over 4 with average rate of change is 0, which is what the computer said it was going to be. So there's just some average rate of change calculations. Now, going back to the graph, got my graph here. So this is the graph of y equals x squared. This is a secant line connecting this point, negative 2, 4, and this point, 2, 4. And what I have over here is the average rate of change that the computer calculated at the second value here, which is at 0. Now, I want you to notice this average rate of change, what happens when I change my second point. It is always changing. And again, I can calculate every one of these by hand. I've got it went down 3 and it went over 3. So that's negative 3 over 3, which gives me negative 1 for my average rate of change. Notice, as my points change, the average rate of change changes. Now, here's an interesting thing. Notice how when my points get very close to each other, that secant line is starting to look like a tangent line. And the tangent line also has a slope. The tangent line slope we call the instantaneous rate of change of the function. But this is not a tangent line. It's very close to a tangent line as I get closer and closer here. So notice, again, I want you to focus here on the average rate of change. It's negative 3.69, negative 7.44, negative 8.67, and negative 3.93. Notice the value is changing. I'm going to go to the other side. Here, the average rate of change is negative 4.58, but as I get closer, bringing my second point now from the left side, notice my average rate of change is becoming technically larger. It's becoming less negative. Negative 4.18, negative 4.12, and it's getting closer and closer to what the tangent line would be. Again, the tangent line is a little bit different than the secant line because the tangent line only crosses the function at that one point when we zoom in. So, we're going to guess what the instantaneous rate of change is. Now notice, I have an average rate of change of negative 4.056 when I'm very close on the left-hand side. And if I get very close on the right-hand side, I have an average rate of change of negative 3.944. This should give you a fairly good guess of what you're going to get. Problem is, when I get right on the point, notice it disappeared. The reason why it disappeared is if my 2 points were connected, notice the whole secant line disappeared. Why? Because what I'm technically saying, let me go here to this, and let's go back to my graph. Just looking at these 2 points. Notice, y2 and y1 are the same. So if I take and attempted an average rate of change, that's not a problem. 4 minus 4, I can have a 0 up there. The problem comes is that the x2 and x1 are the same. negative 2 minus parentheses negative 2. This gives me 0 over 0. You can't divide by 0 because it doesn't mean anything. There's no number on the bottom. So this is an undefined situation. So I can't just bring my 2 points together and tell you what the instantaneous rate of change is. There is no secant line. It has disappeared. But going back to this, if I move it off, and I'm going to show you my calculations. I got my h at 0. That's the distance between the 2 points as we talked about. Now I have some distance in between them. My back in business. Now the secant line appears. I can click on this, and the average rate of change appears. So I can use a secant line to estimate the instantaneous rate of change of the function, but I can't get it perfectly from that. However, if I zoom in, let me just move all of this to the center and zoom in. Okay. As we zoom in, you'll notice something. It allows me to manipulate the situation where I can get my points y2 much closer to y1 and still not be on it. And if I was to continue to zoom in, and I'll zoom in some more, not only can I get my x2 and y2 very, very close to each other, you should notice something very interesting here. And that is my actual parabola, which is a curve, no longer looks like a curve. The whole parabola looks like a straight line because we've zoomed in so much. So I'm just going to take this to here, which is extremely close. And let's see. I'm going to show you the slope of my secant line because it can no longer be displayed. It's not inside. You can't see it anymore. So the slope of my secant line is now negative 3.9979. And as I get closer and closer, you should be able to determine a very reasonable estimate of that instantaneous rate of change or the slope of the tangent line. And I'm going to cross to the other side, and now notice that the slope of that secant line is negative 4 point something and going down. So the lowest I can get it is negative 4.08, which means it's extraordinarily close to negative 4. Go to the other side. It's negative 3.994, which again is incredibly close to negative 4. So from here, I am going to estimate that and let me do it by well, we've already done it. So I'm estimating that my slope of the tangent line is negative 4. Now, this, let me zoom out again. Now we can see the whole parabola. Well, maybe a little too far. So we can see the whole parabola again. We can see the slope of our secant line, which is almost exactly 4. I'm going to turn on the tangent line. And when I say I turn on the tangent line, let's see. The red line is the tangent line. That is the one line that touches just this point and only this point on the graph in this area. So that's my tangent line. And again, my secant line, as I move over and closer and closer and closer to that point, my secant line begins to look more and more like the tangent line. And we can use the slope of the secant line to estimate the slope of the tangent line at negative 4. Again, hopefully this will help you with the homework. You may want to look at the homework questions, come back and watch the lecture again and try to make the connections. What was I doing? I was looking at several average rate of changes so that I could estimate an instantaneous rate of change.